In the last tutorial, we did look at the general, we started looking at the general wave, and then we also covered longitudinal waves and existence of transverse waves, including some examples of transverse waves. But in this tutorial, we'll mostly focus on longitudinal waves and terms used in wave physics. So what is longitudinal wave? So longitudinal wave is a wave whose vibration of particles are parallel to the direction of the wave motion. So if let's consider this one as a particle, this one as a particle. So when the vibration of the particle are moving in this direction, then the direction of the wave motion, direction of wave motion then remember this is the vibration of particles. So when the wave motion is moving like that, then the wave is also, the energy possessing particle is also vibrating in the same direction. It means that the wave I'm dealing with, it is a longitudinal wave. Look at these two lines. Even from the knowledge of mathematics, we're able to see that these two lines are parallel. No wonder we are saying this particle is vibrating parallel to this. But don't forget, the particle can also vibrate like this. Still, these two lines are parallel. So this is the general presentation of vibration of particles when you're dealing with longitudinal waves. Now, what are some of the examples? So examples include sound wave. So when you think of a sound wave, we can think of a speaker that produces sound. Remember, this is the cone of a speaker. Then we see something like this. So it means that this is how a speaker is represented, and this is an example of a transverse wave. Then other than that, we also have wave on a spring. So wave on a spring, again, it is also an example of a transverse wave. So as you can see here, we'll look at this later on, but what you need to know is that this is rarefaction, this is compression, rarefaction, compression, and rarefaction. So existence of waves, existence of longitudinal waves. How do they exist? So longitudinal waves exist in form of compression, and rarefaction. In form of compression, and rarefaction. Not fraction, take note. We are saying faction and not fraction. So the symbol here, it is C. Here the symbol is R. So now let's look at the diagrammatic representation of this. So a diagrammatic representation of compression and rarefaction is this one. So when I draw a vertical lines like this, I'll have another region where particles are very close to each other, then another region where they are far apart, close together, then far apart. So where particles are far apart from each other, it is called rarefaction. Then compression, rarefaction. So we can think of compression look at the word compression. The word compression comes from the word compress. To compress is to squeeze something together. So when we're talking about compression here, think of particles getting close to each other. That is compression. And then the opposite of compression, it is rarefaction. And the same thing applies even to this one, to the speaker that we looked at earlier on. So this is compression, rarefaction, compression, rarefaction, compression. The same thing applies even on a spring. We have rarefaction, compression, rarefaction, compression, rarefaction, and compression. So that is how a longitudinal wave exists. Now, let's move on to the terms used in wave physics. Terms used in wave physics. What are some of the terms that are used in wave physics? Number one, we have we're going to look at counting number of waves. Counting number of waves. Counting number of waves. So to count the number of waves, you have to think of a circle. If this is my circle, then I cut this circle into two equal parts. What am I going to have? I'm going to have one portion there, which is the semicircle. Then I'm also going to have another semicircle. So these two semicircles, they give me one circle. So using this knowledge, number of waves can be counted by counting a crest and a trough. A crest and a trough. So remember, this is a crest. Remember from our previous video, we called this one as a crest and then this one as a trough. So it means that this one is a complete wave, just like what we have seen here. A circle, when it is cut, we can have two semicircles, then another, then that one still gives us a complete wave. So this is a semicircle and another semicircle. So a semicircle and another semicircle gives us one complete wave. What if I happen to have another semicircle? Again, semicircle and semicircle is also giving me one complete wave. So that does not mean that this can only be represented like this. It can also be represented in terms of compression and rarefaction. Look at this one. Then I have this. Then I have this. This one is rarefaction and compression. So this gives me one wave. Then this one also gives me one wave because it is more like a semicircle and another semicircle, giving me one complete wave. Just like here, a semicircle and a semicircle giving me one wave. Again, a semicircle and a semicircle giving me another wave. So here it means that we are forming wave 1, 2. So here we have two waves, two complete waves. Even here we have two complete waves. So that is very important because everything will be based on number of complete waves. So I'll give you the exercise so you can pause the video, then try to solve this one.